Hello, today we're going to learn how to use the bullet solver to simulate this fraction we did last time. So let's jump into Houdini. This is where we left off in the fracture lesson. And we had one fracture that we use for rendering and another version that we use for simulation. And this is the setup we did, except we used this on the right side, but I moved this on over to the left side to make it more clear. Okay, so let's continue from here. So the first thing I do if you look at the simulation side is to transform this up. And I also do the same with the high-res piece. And for this I'm using a reference copy of the node that you can create by right-clicking and select Actions and create reference copy. And that will create a transform that is identical to this one. So if I change this, then the other transform will change as well. Okay, so next we need to prepare attributes for the bullet solver. So let's look at the geometry spreadsheet. So what we had so far is just a position for each packed primitive and a name, if I look at the simulation part, and the name for each primitive. And the bullet solver needs this name to be on the point level instead. So what I'm doing here is using an attribute promote to move this name to this point level. And this is done by using the original class primitive and the new class point for this attribute name. And next we need to set up a whole bunch of attributes. So if you look here, these are the attributes I am defining in the Attribute Wrangle, and Bullet needs all these to be able to work. So I have prepared a little overview so you can see what each attribute does. And these are grouped in different categories, like creation, the bullet shape, primitives, state, deformation, mass, inertia, position, orientation, velocity, collision, contact. And I'm not going to read this through, so you can pause the video and read this when you want to learn more about each attribute. So if we look back in Houdini, the values I have assigned to these is 0 for creation time and 0 for deactivation time. And bullet sleeping 0 for no, and bullet autofit valid 0 for no. And then we have bullet prim T for translation, R for rotation, and S for scale. And these are set to the 0 vector, and the unit vector. And then bullet radius to 1 and bullet length to 1. And again, you will have to check here what these mean. Okay, and then we have the state deformation, and I set an integer active to 1, an integer animated to 0, integer deforming to 0. And you can see up here also the types. So integer bullets, all the flags are integers. And V for vector and F for float. And then we have some mass related attributes. So integer for compute center of mass set to 1, integer compute mass 1, float density 1000, float mass 1000, and float inertial tensor stiffness to 1. And that sounds maybe difficult, so again, just check here. And then we have the rest position vector that I set to the position, and the pivot vector that I set also to the position. And then we have something with a type P, and P is a vector for, or also it can be used for quaternions. So in this case, this is a quaternion that describes the orientation of the attribute. And here I'm using the unit quaternion 0001. And that means no rotation. And then we have some velocity related attributes. So the integer inherit velocity to 0 again for false, and the vector v for velocity is 0 and the vector w for angular velocity is also 0. And then some collision related properties. So I found overlap 0 because it didn't find any collision yet, and float bounce to 0 for no bounciness, and float friction to 1 for full friction. And once we have set up all these attributes on the packed primitives, then we are ready to jump into the simulation. So let's jump into the simulation. And this is very similar to the RBD simulation we set up in the RBD lesson. So I'm only going to explain how this is different from that setup. So the main thing is that we are using the Bullet solver instead of the RBD solver. And this will require, for one thing, all the attributes that we prepared for this object. So if you look here on the object geometry, you can see now we have all these attributes here that the Bullet solver needs. And instead of the physics parameters, we are using these attributes, and also we need a special bullet data that we attach using applied data. So you create one applied data node and then one bullet data node, and here you can select, for example, the type of collision that is used for this object. So now I'm just using a box collision. And also for the packed primitives, we need to use a collider label node. And the collider finder label has to be set to packed object here. And that will again create here under colliders, under object and colliders, then you have your collider label set to packed object. And then we have the gravity as in the RBD lesson, the solver again. And we also have this ground plane setup. And this is almost identical, except that we need this bullet data again. So use an applied data node and attach a bullet data node. And this is just the default. And this is using convex hull, but you could use something else here if you want. And lastly, we have the collision relationship. So this is again left inputs right, so the ground plane will affect the object. And this is a collide relationship. So this is mostly the same as the RBD setup. And again, let's look at this simulation. So here we have the proxy simulation, or the simple version of the geometry. And we are bringing in the result as points again, as we did in the RBD lesson. And then we are stamping the geometry onto the points. Again, if you forgot the properties for DOP Import, remember that these should be create points to represent objects and transform geometry with position data and center at pivot for this to work. And then I'm copying the pieces onto these points. But because we have 2 pieces and 2 points, that would put 2 pieces per point. So that gives us 4 pieces actually. So what I'm doing next is I'm removing the pieces we don't need. So we have only 2 pieces. And this I'm using some vex code to remove points that do not match. And I am using the name attribute on the render version and the name attribute on the simulation version, and matching these. And if they do not match, I delete them. And this leaves only 2 pieces. And now if you look at the result, we have our simulation. And if you remember, we created this line in the last lesson, and this could be used to attach, for example, a glue constraint. So maybe we'll look at that in a later lesson. So again, if you want to learn more about what each attribute does, then just pause the video and read these descriptions. So now you're an expert on creating custom bullet simulations. So I hope this was helpful, and see you next time. Over and out.